Hello, so today we are talking about sampling distributions of means. So the last video we talked about sampling distributions, and this ing means a lot, and so we talked about the difference between samples and sampling. But today we're going to focus on sampling distributions for means. So we're jumping around a little bit. This is section 7.3 in your textbook, so it's skipping over 7.2, which we'll get back to next video. So to start today's lesson on sampling distributions for means, let's just review z-scores and how we do z-scores and how we use table A. So it says, suppose the heights of all American 8th graders follow the n64.5, 2 distribution. And we said that means it's normal with a mean of 64.5 and a standard deviation of 2. So that notation represents normal, mean of 64.5, standard deviation of 2. Well, then the problem says, what is the probability? So probability, I think, what is the probability that a randomly selected 8th grader is shorter than 63 inches? Or what's the probability that x is less than 63? Well, if I think about solving that, I'm given an x, a mean, and a standard deviation. So this is really asking, what's the probability that my z-score is less than 63, or x minus the mean, divided by the standard deviation? And when I do that, I get what's the probability that my z-score is less than negative 0.75. So I draw my nice normal curve. I give 0, 1, 2, 3, negative 1, negative 2, negative 3. And negative 7.5 is going to be right around there. And I want to know what's the probability I'm shorter than that, or that this student is shorter than that. So I'm going to shade everything below. When you go to your normal curve, or your table A, and you look at where z is negative 0.75, you find that area to be 0.2266, or in other words, there is a 22.66% chance that a randomly selected 8th grader is shorter than 63 inches. So this was one sample, a sample of one student, and we looked at the probability x was less than 63. Well, what if I took a sample of students? What if instead of taking one 8th grader, I now take a bigger sample of 5 8th graders or 10 8th graders? That's what we're looking at today. So just to review, if the population mean, proportion, and standard deviation are unknown, so if I don't know these values, like I did in the last example, we're going to use x bar, p hat, and sx to estimate the mean, parameter, and standard deviation. So this is review of last class, but we're going to use this specifically today. So we have two types of sampling distributions, sampling means and sampling proportions. Today we're going to focus on sample means, which is when the problem is talking about means or averages, not percents or proportions. So for sample means, they're describing the sampling distribution of means to the responses of a simple random sample. So there's a lot of words right here. The formulas are our big takeaways. So make sure that you get these down, because these formulas are what we really care about. So suppose that x bar is the mean, so my sample mean from my random sample that we take from a large population, with mu as the mean and sigma as the standard deviation. the mean of the sampling distribution, x bar, so that's sampling distribution, the center, or the average, is going to be centered at the true average of the population. So the mean does not change. Even though I take a sample, the sampling distribution mean is the same as my starting mean. But the standard deviation, or the spread, is going to change. The spread of my sampling distribution for means is my old standard deviation divided by the square root of n. So my spread is going to get smaller when I have a bigger sample, because we talked about last class, the bigger the sample, the less sampling variability your sampling distribution is going to have. And we broke that down last class in more details. So let's start with center and kind of break that down some more and see an example. So it's the same example with the heights for 8th graders, and it tells us that they follow this distribution, n of 64.5, 2. And it says, what would the shape and mean height be for a sample of 10 8th graders? So I know that my mean is 64.5. My standard deviation is 2. It tells me I take a sample of 10 8th graders. Well, if I think about this shape, my population is normal, so the shape is going to stay normal. But the center is my mean, and we said the mean of my sampling distribution equals my regular mean, so my mean is still going to be 64.5. And this is all I have to do for shape and center. The shape is normal because we started out normal. The center is my true center, or the 64.5. For spread, we said it changes a little bit. The smaller my samples, the more spread my data. The bigger my samples, the more consolidated or centered my data is around the true mean. But we have a key point. Key point number 1, and actually the only key point for today, is this thing called the 10% condition. The 10% condition says that the standard deviation formula of sigma of x bar equals sigma over the square root of n, so this formula, can only be used when the population, or capital N, is at least 10 times larger than the size of my sample, or lowercase n. So in symbols, it looks like this. The population is greater than or equal to 10 times my sample size. Sometimes we're going to have to assume this. Sometimes it's going to be given. But this condition has to be met in order for us to use this formula, which then tells us how to find the z-score. So in order to find the z-score, this has to work, which means this has to work. So let's take a look at that example. It says, suppose the heights of all American 8th graders follow this same distribution. So my given standard deviation is 2, and I take a sample of 10 8th graders. So if I want to find the standard deviation of the sampling distribution, or of x bar, that's sigma over the square root of n. But in order to use that, I need to check the 10% condition, which says that capital N is greater than or equal to 10 times lowercase n, or my population is at least 10 times as large as my sample. Well, if I think about the population in this example is all American 8th graders. If you think about all American 8th graders, so every 8th grader in the entire United States of America, do you think that there's more than 10 times 10, or more than 100 of them? Yeah, probably. We think it's safe to assume there's more than 100 8th graders in all of America, so this 10% condition is met. So since this condition is met, I can now keep going with this formula. So sigma of x bar equals 2, or my given standard deviation, over the square root of my sample size, or 2 over the square root of 10, and that gives me 0.632. So this is my new standard deviation, and I could use this formula because this condition was met. So why we do all of this work, the purpose of all this finding the mean and standard deviation of a sampling distribution, is to bring it back to z-scores. We really like z-scores, we really like table A, and so everything we do is working towards that goal of being able to find a probability using table A and using z-scores. So it gives me that same scenario where I have the mean and standard deviation of a normal distribution, but it says what is the probability that a sample of 10 eighth graders has an average height less than 63 inches? So if I think about what this problem's asking me, it's saying what's the probability that the sample mean, or that x bar, is less than 63. Well, that's really different than the first question. The first question was just asking for 1 eighth grader. This is asking for x bar, or the sample mean, of 10 of them. So the probability that x bar is less than or is less than 63 is asking what's the probability that my z-score is less than 63 minus the mean of my sampling distribution, which is 64.5, divided by the standard deviation of my sampling distribution, which we got to be 0.632. So this came from work we did on the last slide for finding the standard deviation. So when I do that computation, the probability z is less than, that gives me negative 2.37. So I've given myself some space right here to draw my normal curve. So negative 2.37 would be right over here. So you can see we're much further from the mean than we were on the first one when we only had a sample of 1. My z-score is way up here. But now that I have a bigger sample, getting a value less than 63 is more extreme or more rare. So this area down here, when we go to table A, is 0.0089. So now this is saying that I only have a 0.89% chance that my sample mean is less than 63. Whereas in part A, there was a 22.6% chance that one person would be shorter than 63. So the bigger my sample, the more extreme being below certain values or being above certain values is going to be. The bigger my sample, the harder it is to stray from my mean, meaning it's much more rare or a much smaller probability. So that's a wrap. We use sampling distributions of means to estimate probabilities, and the normal curve can be used when the population is normally distributed. So this is section 7.3 in your textbook. Look there for more sample problems and to do your problem set. See you next time.